Hi everyone, this is Spectre P, and we are Spectre AI. First, a huge thank you to our viewers for such a response. We've been up a short time and have received hundreds of thousands of views. We are over the moon happy that we are providing needed content that our viewers value. This is video number 9, Time Shift Attacks. In this video, we're going deeper into the vulnerabilities of real quantum networks. We'll look at how detector efficiency curves create timing windows that an attacker can exploit, how Eve can shift photon arrival times to bias Charlie's Bell state outcomes, why this loophole exists even in measurement device-independent QKD, and how researchers are patching these timing flaws in next-gen quantum hardware. Let's break down the time shift attack. The graph you're seeing now shows the detector efficiency curve as a function of arrival time. The vertical axis represents detector efficiency, defined as the fraction of incident photons that are successfully detected. In other words, this is the ratio of detected photons to the total number of photons that arrive at the detector. The horizontal axis represents relative arrival time, measured in normalized units centered around 0. A photon arriving exactly at time 0 reaches the detector when it is at its highest sensitivity. Photons arriving earlier or later fall into regions where the detector becomes less responsive. This curve is shaped by the internal physics of gated detectors used in quantum key distribution and other quantum communication systems. These detectors are typically active only within a narrow window of time, known as the gating window. Inside that window, the bias voltage or current rises sharply, enabling avalanche events to occur efficiently when photons arrive. As the gate opens, the detector begins to respond, then reaches a peak efficiency near the middle of the timing window, and finally drops back down as the gate closes. The resulting shape is similar to a Gaussian profile, with a well-defined maximum at the center. The red marker moving along the curve highlights how the detector responds differently depending on when a photon arrives. Near the center of the curve, the detector is most efficient. Photons arriving in this region are more likely to be registered as valid detection events. On the other hand, photons that arrive earlier or later fall on the sloped regions of the curve, where the detector is less sensitive. Here, even if the photon reaches the detector, it may not produce a measurable avalanche, leading to a lower probability of detection. This timing-dependent efficiency is a critical concept in quantum communication. Many security proofs assume that detection efficiency is uniform across the entire gate, or that any inefficiency is random and symmetric. In practice, however, the physical behavior of detectors introduces asymmetries. These asymmetries are not just implementation details. They form the foundation for real-world timing-based attacks. If an adversary can carefully shift the arrival time of photons, even by a small amount, she can influence the probability of detection in predictable ways. Understanding this curve, and how efficiency varies across time, is essential for recognizing the vulnerabilities that arise in quantum key distribution systems. It sets the stage for the time shift exploit, where an attacker uses these efficiency variations to bias the measurement outcomes of a supposedly secure system like measurement device-independent QKD. Next, we will zoom in on the gating window itself and see exactly how this timing dependence emerges at the hardware level. This graph introduces one of the most important conceptual gaps in quantum key distribution security: the difference between how detectors are assumed to behave in theoretical models and how they actually behave in real hardware. Here, the yellow horizontal line represents the idealized detector efficiency curve used in many security proofs. In that model, the detector is assumed to register incoming photons with a constant probability throughout the entire timing window. In other words, the detector is treated as if every photon that arrives during its gate has the same chance of being detected, regardless of whether the photon arrives early, late, or perfectly centered. This simplification makes the mathematics elegant, but it does not reflect what happens inside real optical detectors. Superimposed on that idealized curve, drawn in cyan, is the actual detector efficiency curve measured in laboratory systems. Unlike the flat theoretical model, real detectors have a sharply peaked response centered around the middle of the gate. Photons that arrive at this central region are detected with very high probability, while photons arriving earlier or later fall on the sloping sides of the curve, where the detector sensitivity is lower. This difference arises from the physics of avalanche photodiodes and superconducting nanowire detectors, which do not turn on instantaneously or uniformly. They ramp up to a maximum bias condition and then decay, producing a time-dependent detection probability that naturally takes on a peaked shape. The shaded red region highlights the disagreement between the theoretical and real curves. This shaded area represents what we call the exploitable gap. The term refers to the fact that security proofs built on the idealized model implicitly assume the detector always responds uniformly to all photons arriving within the gate. However, in real systems, photons arriving on the tails of the efficiency curve experience a significantly reduced probability of detection. This means that an adversary who can precisely control or manipulate the photon arrival time can steer detection events into regions where the detector behaves differently than the model assumes. These exploitable gaps exist on both sides of the peak, one on the early arrival side and one on the late arrival side. In these regions, even a small intentional time shift applied by an attacker can have a disproportionately large effect on the probability that a photon will be detected. Because the security analysis assumes a flat efficiency, it does not account for the way these time-dependent variations can bias detection outcomes. As a result, the discrepancy between the yellow ideal model and the real cyan curve becomes a foothold for timing-based attacks. Understanding this divergence between theory and practice is essential, because most quantum communication protocols derive their security by assuming accurate detector models. If the detector does not behave as assumed, the adversary gains a powerful tool. She can shape the statistical distribution of detection events by manipulating timing. These exploitable gaps are therefore the foundation of several known time-shift attacks, where Eve introduces deliberate delays or advances to the photons to force the legitimate parties into sampling regions of the detector response curve that they do not realize are insecure. Next, we will examine how Eve uses these exploitable gaps to bias measurement device-independent QKD systems, despite the fact that those systems are designed specifically to remove detector vulnerabilities. By exploiting the timing asymmetry rather than detector control, she bypasses the assumptions built into the security model and manipulates the Bell state outcomes without ever touching the measurement device directly. In this depiction, we evaluate the detector's efficiency at specific arrival times to understand how sharply the hardware response changes across the gating interval. The efficiency function shown represents the photon's arrival time, and sigma controls the width of the detector's response profile. For this example, sigma is set to 0.30, which corresponds to a moderately narrow detection window consistent with the behavior of gated avalanche photodiodes and superconducting nanowire detectors. The efficiency function expresses, for any arrival time t, the probability that an incoming photon will be successfully detected. To see how this works numerically, we begin by evaluating the function at the center of the detector's active region. When a photon arrives exactly at t equals 0, the exponent becomes 0, and the efficiency evaluates to 1. This corresponds to perfect or near-perfect detection probability, which aligns with the peak of the Gaussian response curve shown earlier. Next, we examine a photon that arrives slightly off-center at t equals 0.40. Plugging this value into the efficiency function gives a probability of 0.169. This means that at this shoulder position on the timing curve, the probability of detection has fallen from unity to about 17%. Even a modest timing offset, therefore, produces a dramatic reduction in sensitivity, revealing how steeply real detectors decline outside the center of their gating window. Finally, we compare the two results directly by forming a bias factor, defined as the ratio of the central efficiency to the off-center efficiency. Dividing 1 by 0.169 yields approximately 5.91, which rounds naturally to 6. This means a photon arriving at the center of the detector's active region is detected almost 6 times more often than one arriving only 4/10 of a timing unit away. Such an imbalance is not a small perturbation. It is a profound asymmetry in the sampling of detection events. This sensitivity to timing is precisely what an attacker can manipulate, and in the next depiction we will examine how Eve leverages these probability differences to bias the receiver's measurements while remaining hidden within normal channel loss. In this depiction, we illustrate how an eavesdropper can exploit the time-dependent response of a realistic detector to bias which events are ultimately observed by the receiver. The efficiency curve shown here represents the probability that a photon is successfully detected as a function of its arrival time. As established earlier, this curve is sharply peaked around the center of the detection gate, where the detection probability is effectively equal to 1, and it falls off rapidly toward the shoulders, where it is only about 0.169. This decline reflects a fundamental physical limitation of the hardware rather than a flaw in implementation, and it becomes the foundation of a subtle but powerful timing attack. Eve's strategy is straightforward. She shifts the arrival time of photons to place them deliberately on regions of the detector response curve that serve her interests. Photons corresponding to basis-matched states are steered toward the peak of the curve, arriving at t equals 0, where the detector has very high sensitivity. These photons almost always produce a detection event, and therefore disproportionately populate the dataset that Charlie uses for key generation. In contrast, photons corresponding to basis-mismatched states are shifted slightly forward or backward in time, so they arrive near t equals plus or minus 0.40 on the low-efficiency shoulders of the response curve. Because the detection probability in these regions is only about 17%, the mismatched states rarely survive detection and thus contribute much less frequently to the observed outcomes. The animation highlights this process visually. The matched photon is shown landing at the center of the gate and remaining bright, representing its high likelihood of being detected. The two mismatched photons are shown arriving at the shoulders and gradually fading, indicating that they are absorbed or lost with high probability. Once the system has settled into this pattern, the corresponding probabilities appear numerically. P-match, evaluated at time equals 0, is approximately 1.000, while P-mismatch, evaluated at time equals 0.40, is approximately 0.169. The ratio of these two quantities, known as the bias factor, is nearly 6. This means that a photon arriving at the center is detected almost 6 times more often than a photon arriving only a modest distance away. The consequence of this imbalance is that the sample of detection events Charlie records is no longer representative of the underlying quantum ensemble transmitted by Alice and Bob. Instead, it is systematically skewed in favor of the events that Eve wants preserved and against the ones she wants suppressed. Crucially, this manipulation does not require Eve to alter the quantum states themselves or to interfere with Charlie's measurement device. She exploits only the timing asymmetry in the detector's response. From the receiver's perspective, the reduced detection of certain events appears indistinguishable from ordinary channel loss, making the attack extremely difficult to identify without explicitly monitoring arrival time statistics. This visualization therefore demonstrates not only the mechanics of the exploit, but also the vulnerability created when real detector behavior diverges from the idealized model assumed in many security proofs. In this depiction, we see how Eve manipulates the timing of individual quantum signals to bias which events Charlie ultimately detects. 3 pulses enter Eve's interception point. The single bright cyan pulse represents a basis-matched signal, the kind of photon Eve wants Charlie to detect. The 2 red pulses represent mismatched or undesired signals. As soon as Eve receives the signals, she discards one of the mismatched red pulses immediately. This reflects the fact that mismatched states contribute nothing useful to Eve and would simply generate errors if Charlie detected them. The remaining 2 pulses, 1 cyan and 1 red, are then routed forward. Eve forwards the surviving red pulse, but intentionally shifts its timing so that it arrives during a low-efficiency region of Charlie's detector. In the animation, this is shown by the red pulse fading and fragmenting as it travels. Even though it reaches the detector first, it arrives at the wrong time, and the detector effectively ignores it. The cyan pulse takes a different path. Eve times it precisely so that it reaches Charlie during the peak of the detector's sensitivity window. It remains bright, focused, and coherent as it travels, and when it reaches the detector, it triggers a strong detection event. This is exactly what Eve wants. The detector records the matched signal but misses the mismatched one. The visual metaphor illustrates the core idea of the timing attack. Eve suppresses the signals she doesn't want Charlie to see, and she promotes the ones she does, simply by altering their arrival times. Although several pulses enter the system, only the well-timed cyan pulse survives to influence Charlie's measurement statistics. Up to this point, we learned the main concept. We saw how Eve biases which detection events survive by shifting the timing of different pulses. Now that she controls the detection sample, the next steps in the protocol begin working in her favor. For the remainder of the video, we'll look at how the public basis announcements, error correction messages, and finally, privacy amplification all leak additional structure. Enough for Eve to reconstruct the key. In this matrix, we look at what the public basis announcements reveal once Eve has already biased which detections survive. Each row in the matrix represents a different transmission round, showing the basis Alice used to prepare her qubit, the basis Bob used to measure it, whether Charlie recorded a detection event, and whether that round becomes part of the raw key after sifting. The key observation is that basis information is public. Alice and Bob announce their basis choices openly, and anyone listening, including Eve, can match these announcements to the rounds that produced detections. Because Eve has forced only her preferred arrivals to survive, she already knows which of these rounds produced valid, high-efficiency clicks. She can now watch the public sifting process unfold in real time. When Alice and Bob used different bases, the measurements are discarded, and those rounds never contribute to the raw key. But when their bases match and Charlie records a detection, that bit is kept. These matched basis detections are highlighted in cyan, and they form the backbone of the raw key shared by Alice and Bob. Since Eve controlled which detections occurred in the first place, she knows exactly which rows in this table will survive sifting. The public announcements simply label each surviving detection with its basis, allowing Eve to map each detection event onto its corresponding bit position. At this point, she has a structurally accurate picture of the raw key before error correction even begins. In this depiction, we look at how the error correction stage of the protocol leaks information about the raw key. On the left, we have 3 positions from the key, labeled B1, B2, and B3. These are simply bits in the order they appear before privacy amplification. During error correction, Alice and Bob exchange small amounts of information to help Bob fix any differences between his bit string and Alice's. The important detail is that these messages are public. Everyone hears them, including Eve. Even though the messages don't reveal any bits directly, they do reveal relationships between bits. And that turns out to be enough. In this example, Alice and Bob announce two parity constraints. Think of these as statements about how the three bits relate to each other. Eve doesn't know the values of B1, B2, or B3 yet, but she does know the two rules that the three bits must satisfy. Eve starts with the second rule, which tells her that B2 and B3 must be the same. That alone is already useful, because anytime two unknowns are known to match, it reduces the number of possibilities she has to consider. Once she knows that B2 and B3 are equal, she goes back to the first rule. When she substitutes that information into the first rule, the relationship becomes even simpler. Two of the terms cancel each other out, leaving only B1 on one side and a known value on the other. From that single remaining condition, Eve can determine the exact value of B1 with certainty. What's remarkable is that Eve has learned one of the raw key bits even though she never touched that bit, never measured it, and never learned anything about the values of B2 or B3 individually. She learned B1 entirely from the structure of the error correction messages. This example demonstrates a broader point. Every parity message, even if it appears harmless, removes a little uncertainty. When thousands or millions of these relationships are published, Eve can gradually solve for more and more of the raw key, long before privacy amplification attempts to compress it. In this depiction, we're looking at what privacy amplification is supposed to accomplish and why it fails when Eve has biased the detection statistics earlier in the protocol. On the left, we see Alice and Bob's raw key, 10 bits long. Eve does not know every bit, but she doesn't need to. Because she forced the detector to favor certain outcomes, she already knows several positions with certainty. Those bits line up perfectly. The remaining positions are unknown to her, so they appear as blanks. If we measure the similarity between the two keys at this stage, the correlation is only about 50%. That means Eve has fragments of knowledge scattered throughout the key, but nothing close to a full reconstruction. Now look at the right side. This is what happens after privacy amplification. Alice and Bob apply a hash function to compress the raw key into a shorter, final key. Under normal conditions, hashing destroys Eve's partial knowledge. But in this attack, the hash behaves differently. The hash is a deterministic function. So if Eve already knows some of the raw bits with certainty and has high confidence guesses about others, her partial knowledge becomes concentrated when the key is compressed. In other words, hashing doesn't erase her information. It amplifies it. This is why, after hashing, Eve's predicted key aligns with Alice and Bob's final key in 9 out of 10 positions. The correlation jumps from 50% to 90%. The hash has taken a handful of scattered correct bits and turned them into an almost perfect match. The key point is this: privacy amplification assumes Eve's knowledge is random and unstructured, but Eve's timing attack gives her structured, biased information. And deterministic hashing preserves that structure rather than destroying it. So instead of reducing Eve's knowledge, hashing transforms her partial insight into a nearly complete reconstruction of the final secret key. In this lesson, we've seen how a very small, very subtle hardware imperfection can unravel the entire security of a quantum key distribution system. Real detectors are not ideal. Their sensitivity depends strongly on exactly when a photon arrives. The center of the detection window is extremely responsive, while the edges are far less responsive. Eve takes advantage of this physical weakness. By shifting the arrival times of photons, she can quietly control which ones are likely to be detected. She sends the matched photons into the high-efficiency region, and she pushes the mismatched photons into regions where the detector almost never fires. As a result, The raw detection record that Charlie sees is already biased before any protocol steps even begin. Once Alice and Bob announce their measurement bases in public, Eve immediately learns which of her promoted detections become raw key bits. She now knows exactly which positions in the raw key stream matter. During error correction, Alice and Bob exchange parity information to reconcile their keys. But those parity messages leak additional structure. With only a couple of parity equations, Eve can actually solve for specific raw key bits she never measured. Finally, privacy amplification fails in this setting because Eve's knowledge is not random noise. It is structured and aligned with the way hashing works. When Alice and Bob compress the raw key to produce a shorter final key, Eve's partial knowledge is compressed in the same direction, giving her a highly correlated copy of the final key. The bottom line is this: by manipulating timing alone, Eve can reconstruct Alice and Bob's final key with high accuracy, without ever touching the detector or directly measuring most of the photons. Thank you so much for watching. If you enjoyed this video, make sure to like and subscribe. It really helps the channel grow, and it's easy, quick, and free for you. And if you want to take the next step, visit spectreai.ai, where we built 55 real, hands-on quantum security labs so you can learn real-life quantum security. Everything you learn in these videos have labs associated with them so you can learn by doing. You can also check out our full book series on Amazon for deeper study. The books go with the online labs. Leave a comment and tell us what topic you want to explore next. We read every one of them. Thanks again for watching, and we'll see you in the next video.